All right, now that we've kind of taken a look at the fundamental equations with fiber optic waveguides, let's look at how the signal is processed, and that kind of leads us into a discussion of some of the losses. All right, so this slide just kind of goes over the process in which optical fibers are used in telecommunications. That's basically to send digital signal through the fiber optics from one terminal to another. So the first thing that has to be done is the signal, the electronic signal, has to be coded digitally so that we can actually transport it. And so it's done coded digitally and then converted into an optical signal. So we're not going to cover that. That's not really part of this optical properties section, but it's converted into an optical signal. From there, that signal is what is basically consists of high frequency laser pulses. So that's the light source that we talked about when we talked about how a waveguide was composed. And so, basically you have, multiple fiber optic cables over here, each of them communicating data with these laser pulses. So then, as the light travels through the waveguide, it's bouncing around at that angle that we talked about in order to reflect. But because these materials aren't perfect, the signal signal broadens and also weakens, and so there tends to be points along the waveguide in which we re-amplify the signal. So there's kind of a amplifiers along the way. So we'll talk more about this part in a second. And from there, once it reaches the end, that signal is received and then converted back into electronic signal. And that's the information that we want. All right, so let's think about those losses for a second. One thing I want to let you know about is when we talk about optical properties and we talk about these optical fibers, losses are typically communicated in a different way. So we call them attenuation. That means that's just another term for losses. And we express that in terms of decibels. So that's lowercase d, capital B. So that's our way of communicating losses in the signal over the sort of the waveguide journey. And then that's also known as attenuation. So again, attenuation, just another term for loss. And so decibels is just a log-based way of communicating the loss in signal. And so it's 10 times the log of the output power minus the input power, right? So we're losing signal, so this power output is going to be lower than the power input. And so we can also think about that as a ratio of the intensities as well. So instead of power, we can think of it as intensity. So initial intensity is I naught, and then the output intensity is I t, but it's 10 times the log of that ratio, and that is what we know of as decibels. All right, so let's think about some things that can cause this loss. So we know that the material is not perfect, right? And when we talked about optical interaction with ceramics, we talked about scattering, right? So that's going to be one of the potential losses. Absorption, that's going to be another one, and then deterioration. Basically, these contribute to the attenuation in fiber optics. And so this plot here just kind of shows some of the different losses as a function of wavelength. So at very low wavelengths, we tend to get a lot of scattering from electron transitions, and so our losses are really high. And then at the much higher wavelengths, we get a lot of molecular vibrations in the material. And in between, we can have different groups within the material, they can also cause losses from scattering or absorption. And so if you look at some of those, iron, hydroxides, copper, so impurities in the glass, if it's not completely pure, can also cause absorption. So we typically want very pure materials without, iron impurities, hydroxyl groups, copper, etc. So all of those things can cause it. And it's very wavelength dependent too. So another goal is to potentially find more optimal wavelengths for that as well. Okay, so yeah, so above 5 microns, absorptions in the SiO-Si bond network. And so that's something that we can't really control, right? If we're looking at a glass fiber, we're always going to have that bond network. And so typically that kind of rules out communications with wavelengths over 5 microns because that's something we can't necessarily control. Two, so again, trace amounts of impurities, transition metal oxides, these are always bad. They can cause absorption from electronic transitions. Again, we talked about this in the last lecture. This gives us coloration, but again, it leads to absorption, which is not something we want in this network. And also SiOH in the bond, in the glass structure, that can have significant absorption as well. So we want to try to eliminate those impurities as well. So it's kind of estimated that 1 part per billion of these impurities leads to a 1 decibel per kilometer loss. And so we'll talk about how significant that is, but that's we're talking about 1 part per billion. So these things have to be really pure in order to get low loss or low attenuation. And then again, like we talked about, electronic transitions below 0.5 become significant as well. And so that's kind of unavoidable. So we're kind of looking at this narrow range in which we get less losses, but that less losses it assumes that we don't have a lot of impurity materials either. All right. Another thing that can cause issues, which I've listed here, any density or compositional fluctuations that we have in the glass can lead to scattering. If we have differences, density and composition can cause differences in refractive index, so that's going to be bad, and so we want to eliminate those as well. All right, so let's talk about some of the different types. So I think everybody's probably seen these really cheap polymer fiber optics. If you've ever owned like a really cheap one of these Christmas tree type things that changes color and so forth, excuse me. Those are obviously, have their applications like these consumer products, but overall these aren't that great because they can only transport light short distances because they have strong attenuation, heavy losses along the way. So these aren't great for telecommunications when we're talking about communicating data with limited losses. And again, pores, inclusions, dust, anything like that, irregularities in the fiber, all of this is going to cause scattering, which we saw in the previous lecture was bad for that, but can also is very bad for this. All right, we've been talking about these attenuations, these losses, and so why don't I'm going to have you look at an example of this and see what these numbers kind of mean. So we have, imagine we have an optical communication network, and our ratio of the light intensity, so this is our loss, our ratio of the light intensity at the source and the detector is 10 to the minus 6. So what I want you to do is take that and see if you can calculate the losses in decibels in this system, and then imagine we have a attenuation of ordinary soda lime glass, and I'm giving you the attenuation there. And for that one, see if you can calculate what fraction the light signal will be lost over 1 meter. So this is essentially in terms of distance, whereas this first one is just looking at decibels. So take a minute and see if you can solve those two questions. All right, so now we're back with this one. So let's take a look at these two questions. And again, I put this here just to kind of throw you off a little bit, have you listen to the video. So here, again, this is just the same thing, just kind of showing you the two questions I asked. So again, the first one gave you the ratio of 10 to the minus 6 and asked you to get that in decibels. So again, our decibel equation is 10 log of the ratio of intensities. So we're talking 10 to the minus 6. You don't even need the 1 there. And that's going to be 60 decibels. And so you'll notice the negative there, but we just refer to this as 60 decibels. Don't really usually say the negative part, but to keep in mind that is there. Okay, so that gives us the losses in a commonly used form. For the other one, for the other part, it says the attenuation. So it's giving you it in decibels per kilometer of 3,000 decibels per kilometer, and it asks you to determine what fraction of light signal is lost over 1 meter. So 1 meter in terms of kilometers is 0.001. And so if we multiply that by the decibels per kilometer, then that will give us decibels. And so that means that for 1 meter, we have 3 decibel loss, right? So -3. So then if we plug that back into the equation from above and solve for the ratio, so IT over I naught, then that's going to give us 0.5. So effectively, what this tells us, since we have 3,000 decibel loss over 1 kilometer, this tells us that in 1 meter, so again, 3 feet, meter stick, 1 meter, we lose 3 decimals, which translates to a 50%, 0.5 reduction in the intensity. So our original intensity has reduced by half over this 1 meter. So that is heavy losses. So that kind of gives you a scale, because we are using the decibel, the log scale. So that kind of gives you an idea of how much is lost. All right, so speaking of those sort of losses and how much data can be therefore communicated, this is just kind of, for your sort of just interest, is to kind of go over a brief history of the transmission rates. And so transmission rates are obviously going to be dependent on how much losses there are. And so the more losses we have, the less data that we can transmit per second. And so starting off in the 70s, so in 1978, we could transfer about 1 kilobyte per second for 10 kilometer system, or 10 kilometer per second. So then if we go 3 years later, that jumps up order of magnitude to 100 kilometer per second. And we did that by reducing the size of the core when we had single mode fibers, and also having different transmitters and receivers that we could use 1.3 micron light, again trying to optimize the wavelength of the light for the system. A year later, we can get hundreds of kilometers per second, so we're a lot higher within a year, and we did that by increasing silica purity. So again, impurities are a big issue here, so if we can increase purity, we can increase this. And then by the late 80s, we got thousands of kilometer per second, and the way we did that is by adding these self-amplifying signals. So we get these signals and they can self-amplify instead of having to add something into the line. And that is done by europium doped glass. And I want to talk a little bit about that in a second. All right. So europium doped. So these ions, Er3+, are added into the line. And what that does is amplifies the signal, because what it can do is it can absorb IR radiation and transfer that to the weak signal. So IR isn't used for the data transmission. It's used in conjunction with these ions to amplify the signal. So just to kind of illustrate the process in which this happens. So we have these ER3+ absorbs IR radiation, and that's produced by the laser chip. And that has a wavelength of 1.48 or 0.98 microns. This light excites those ions, and it can excite those excited ions, then transfer their energy to the weakened signal. And so that's how we get this amplification. And so this excitation that we have amplifies the signal. So that means that we don't have to have anything in line to sort of boost the signal, because this is doing it for us. And so it eliminates the need for regeneration, repeaters, or anything like that that disrupts the path, and it makes longer cables possible. So this was a big advancement, and what allowed us to get to this thousands of kilobit kilometer per second.